Thanks. All right. Thanks for coming and listening to my talk. I'm going to talk about shape as an organizing principle for data. And what I want to describe is a way to record and understand and remember shape in very high-dimensional spaces and complicated spaces. So what's the problem with data? Well, the problem is that it's complicated, right? It's complicated because it's big data, right? People talk a lot about volume and velocity, but complexity comes from a lot of places. We also see, like, we had some presenters earlier talk about graphs. Graphs are sort of very complicated spaces. There's also complexity comes from, let's say, just rich feature sets. For example, if you think of genetic data, in a lot of genetic data sets, you might, let's say, SNP data, you might have 1 million features or columns, but just hundreds or maybe thousands of patients or samples or points in your data set. And that's very complicated because there's interdependencies and connections between the gene, the activations and the genetic expressions and all these things. And you may not have a lot of data. So I want to think about complexity, not just complexity because of size, but complexity because of rich feature sets, complexity because of underlying connections, such as a graph. All of those will fall kind of within the bucket of things I'm talking about. So what do you want to do? How do you handle complexity? Well, in the example here that I'm kind of drawing is a room full of people talking. And when you walk into a room like that, you hear a bunch of white noise, right? It's the voices of all the people talking, melding together. And what you'd like to do is understand, a summary, say, of the different conversations that are happening. Or maybe you want to zoom in on a particular conversation. But generally speaking, you're not trying to find out what every single conversation is about, right? Summaries are more interesting and more useful than retaining all of the information. So I'm going to talk to you about a particular kind of summary. So I'm saying summary in a technical sense. I'm going to talk about topological summaries. So a topological summary is a recording of certain aspects of a data cloud while forgetting other aspects. Right? That's what a summary is. It's something that remembers some things and forgets others. So I'm going to describe to you how to create topological summaries. I'm going to describe to you why you'd want to create them. And then hopefully at the end, I'm going to show you a bunch of problems that we at Ayasdi have solved using topological summaries. Right? This is not just, this sort of starts off as a math talk, but it ends up as kind of a practical application talk. Okay, so this is our guiding principle. Shape as an organizing, I'm using the word principle twice. This is our guiding statement. Shape as the organizing principle for data. So this is something that everybody here is familiar with, but maybe they haven't thought about it in these terms. So here I drew a line, right? A scatter plot of a slightly noisy line in the plane. Well, line is a kind of shape, right? It's a particularly useful one. It's even a very common one. We like it because we can do linear regression, we can do prediction, etc. All of that, the power of linear regression comes from the shape, the fact that it's a line. It's a linear space, right? Well, that's not the only kind of shape that you're used to dealing with. So here we have some clusters. And clusters are also a kind of shape. Now, maybe you're thinking, clusters, are they really shapes? I would argue, in fact, and in fact, sort of mathematicians would say, the number of connected components of something is the most primitive descriptor of shape, right? It's sort of the most basic thing you could say about a shape is how many pieces does it break up into? Clustering is all about determining the number of pieces. Right? And it's a study of a kind of property of shape. Here's another shape. If you see this in your data, typically you're going to have periodic signals. Something's going to be periodic with respect to some parameter, maybe time, maybe pressure, maybe something else, right? Circles are another kind of shape. You're all familiar with them. They represent periodic behavior. And then finally, here's a shape maybe you haven't thought about quite so much, a T-junction or the Mercedes sign. The way I would think about this is that there are 3 segments in your data. So segments are something weaker than say classes in your data because there's a continuous movement between the different segments. An example of this would be something like diabetes, where you can have type 1 or type 2 diabetes, but you really don't just have type 1 diabetes. You're on some kind of spectrum of having type 1 diabetes, right? So it's not that you are all of a sudden diabetic, it's that you move in a continuous fashion along the spectrum. So that's another aspect that, of shape. So you notice here, I have 4 really simple shapes up on the board, but each of them is kind of a whole domain of analytics, right? And the first one, linear regression, is like an industry. People make careers just off of doing linear regression. The second one, clustering, right? It's one of the most common machine learning tasks is clustering or classification. The third one, right, periodic signals, right, signal processing, Fourier series, spectrum, all this stuff, right? There's like careers and textbooks and whole sections of the library devoted to studying that shape. And then the fourth one is maybe a little bit more obscure. Well, the problem with these techniques is that you have to know ahead of time which of these 4 boxes that you're in. And your problem needs to divide, kind of segment nicely into one of these boxes. Am I dealing in a periodic signal world, or am I dealing with linear regression, right? The problem is that, with complexity and high dimensional spaces, you don't know ahead of time what situation you're in. And in certain regions of the space, in certain kind of regions of some parameter space, you may be dealing with a periodic phenomena, and in other regions, you're dealing with linear regression. Right? This is what complexity is about. It's that the simple models, not only do you not know what simple model to apply to your problem, but you don't even really know you don't even really know if there is one simple model to describe the problem. So what we want then, we want a way to discover the underlying structure without assuming first what it is, right? We want the data, right, the problem, the data we have on the problem to tell us what the important underlying structures are. And that's the purpose of a summary. So TDA, or topological data analysis, is a way of looking at the data and having it tell you what the model is, what the behaviors, what the phenomena are in the data. Okay, so that's why we want to do this. But now I'm going to show you how we do this, how we generate, what is a topological summary, and how do I build it. I'm going to go through this kind of fast. And that's okay, because there's lots of material online on our website, or you can find me on YouTube giving the same talk, but having 3 times as much time, where I go through this very slowly. So I'm going to go through it sort of fast right now. So this here is this pair of pants is my data space, and I'm going to think of it as my data points as sampling the surface of this pair of pants. And I'm going to start with a function f. So a function is an assignment of a real value or a number to every point of the data. And the way I've drawn it, that function is just the height function. I'm just projecting the data straight across onto that line segment. What I'm going to do is I'm going to take open sets in the line segment. I'm going to look at the inverse image of the open set. So U1 is a little piece of the line segment. I look at all the points that map to U1. It's the bottom or the trunk of that pair of pants. And within that open set, I'm going to do clustering. And so the way I've drawn it, I found 2 clusters. So on the far right, I'm going to draw 2 dots for the 2 clusters. Now I'm going to do that again, but I'm going to take a covering of the range of this function, meaning that my open sets are going to overlap. So I take this as oversampling. So I take another set U2. Again, I look at the inverse image of U2. I do clustering in the inverse image of U2. And I find 2 more clusters again. Now notice, because the open sets overlapped in the range, there's going to be some piece of the domain of the function where there are points in both U1 and U2. That means there are points that go to one cluster in U1, and those same points go to a different cluster in U2. When that happens, I'm going to draw edges between the clusters. And now I'm just going to I'm going to cover the complete range of this function, and I'm going to just go and do this. So this is what I get. This is a summary. So what do I mean by this is a summary? Well, I mean that I've remembered something about the space that I started with. I remembered that the pair of pants has a kind of Y shape to it. But I haven't remembered everything. I've forgotten some things too, right? There's a hole an empty hole in the pair of pants. There's this circle, this void, and I forgot about that void, right? I didn't remember it in this process. And that's the point of this. I'm going to remember some things about the shape, right? Essential things, right? When you look at this Y, the fact that there's a trunk and 2 legs, that's kind of an essential aspect of the data. But I'm going to forget something else. So what does that mean? Well, luckily, right, the summary was done with respect to this function f. And there are lots of functions out there. So by using different functions, I get different summaries. And I build up incrementally more information about the shape. Right? The summary, as I drew it, is a kind of, it's a graph, but it's actually sort of, in a certain sense, one-dimensional. And it's very easy to understand. It can compress very high-dimensional spaces with complex behaviors down into simple stories, simple things that I can understand. And I'm going to use different lenses to get different pictures of the data. So here's an example where I've taken a kind of limiting case of, right, I've replaced that network there that you saw at the beginning with this Y, right? You can imagine that being a very fine network where you just can't see the nodes and the edges. And here I've drawn a different function, G, and what the summary looks like with respect to G. Now you could build it, if you remember how I said how to build the summary, you take a point in the range, in the range of the function, you take an open set, you take the inverse image, you cluster the inverse image, you can see that you get this eyeglasses for a densely sampled pair of pants. The eyeglasses remember something different about the pants, right? They remember the holes, they forget the trunk and the 2 legs. Right? Different summaries will remember different things about the data. Okay, so lenses come, these are the functions that we do summaries with respect to. Well, lenses come from our regular toolkit for analytics. Okay, so statistics, right? Anytime you can calculate a number for a point, density, the mean of the columns that make up the point, nth moments, variance, etc. Right? All of those are the assignments of values to points, to functions. They make great summaries. Machine learning provides another source of summaries: PCA, SVDs, autoencoders, various sorts of dimensionality reduction. These are all good lenses. And then there's also geometry. So the point of this is that this topological machine that I've described kind of is a framework that's going to eat all of the other analytic domains, right? Geometry, statistics, machine learning, they all produce functions. They can all be put into the machine. But the machine is going to get higher fidelity out of those methods. It's okay if I haven't convinced you of that yet. I'll try to by the end of the talk, but we'll see how far we get. Okay, so why topology? So a lot of you, maybe you're in school or you went to school, you studied data analysis, you studied statistics, you studied computer science, you studied maybe machine learning. One thing that was not on your curriculum was topology, right? So you might be saying, well, why topology? Why would I think that topology would be a good source for a framework for data analytics? Well, one way is we've already seen actually in our talks, right? We have the people who talk about data matrices, and we have the people who talk about graphs, right? They're both topological spaces. So from that sense, the method, the machine I've described is very general. It's indifferent to whether you're studying graphs or data matrices or, almost any problem you can think of. And in fact, topology is the weakest notion of shape, right? So it has as few assumptions as possible go into what you need to define a shape. And that's what makes it so powerful. But on a more concrete level, there are three properties of topology that make it well suited for data analysis. So I'm going to go through them in turn with kind of toy examples. Now they're really simple examples because they're designed to really just pull out exactly the information that we want, sort of the concept. So let's just go through them. Coordinate invariance. So coordinate invariance, what does that mean? The topology of a shape doesn't depend on the coordinates you use to describe it. I could describe your location in the US by latitude, longitude. I could describe your location in the US by, say, an address, right? It doesn't matter what coordinates I've used to describe your location, right? The shape of the US doesn't change if you're being described as an address or as a latitude, longitude. So different features can describe the same phenomena, different feature sets, right? And also, we frequently alter coordinates while we do data analysis, scaling, whitening, rotations, etc. Now, what we hope is that these things don't, right? The things we're interested in better not depend on our choice of scale, rotation, or whitening, right? The things we care about are always coordinate independent, right? This is like when you study physics, right? You talk about the boiling temperature of water. It boils at a certain temperature, no matter if I describe it in Celsius or Kelvin or Fahrenheit, right? Those are just different coordinates on a phenomena. And that's what data problems are, features in your data problems. So just coordinates on some phenomena that you're trying to study. And we don't want, the things we care about don't depend on these coordinates. Topology is built to not use, right? It's designed around ignoring the things that depend on coordinates. So here's a concrete example. So these are one of these networks that we just saw earlier on. These are patients with breast cancer. And it's from two different clinical studies measuring different sets of genes from the patients using different machines to do the measurements. So different people, different machines, different genes, but we have the same patient segmentation, right? So there's a space of cancer that you're studying with these coordinates, and you can use one set of genes in one patient measured with one kind of device, or a different set of patients, different genes, different device, but you find the same underlying phenomena, right? This is coordinate invariance. I can match up those patient subpopulations without having any way to compare them. Okay, property number 2, deformation invariance. Okay, topological features don't change when you stretch or distort the data. So the point here is where we can be sloppier. We can be sloppier with our data problems. It's going to give us noise resistance, less pre-processing, and more robust and stable answers. So here's a very simple example. Like I said, I'm keeping things very simple in this first portion. I have two lines. I have a kind of clean-looking line, and I have a noisy line. I'm going to put it through the topological machine where I use the x-axis as a coordinate. Well, when I do that, I actually find out that one of my lines wasn't a line at all, it was a circle. So this is part of the bias that we talked about at the beginning, right? We want the machine to not just feed us what we tell it to feed us, right? Here I thought it was a line. It looked like a line. It had, 99.999 percent correlation or whatever you want to say, but it was actually a circle, right? It was a very thin, stretched out circle. We want the machine to not be fooled by our own biases. Okay, here's another example, 2 intertwined spirals. I can do the same thing. The machine pulls out 2 lines because the twisting up of the 2 spirals is just a deformation. When you put it through the machine, you use the x-coordinate again as the function that you're making the summary with respect to, you're going to get 2 lines. So finally, something I've been suppressing a little bit is that this process replaces a metric space with a combinatorial representation or a combinatorial summary. It's called a simplicial complex. So this is a technical math term. Well, the reason you do that is that the data becomes easier to manage, query, and understand while we're maintaining the essential features of the data set. And you can leverage known algorithms. So here's an example of compressed representation. Right? 2 different kinds of maps are used for different phenomena. In the first case, we have a road map, right? It's this compressed representation of the country, of the US. In the second, we have a geologic map. It's a different kind of compressed representation. It's a different summary. So you use different summaries of your data to solve different problems, to answer different questions. But you wouldn't ever go out and remeasure the highway system when you wanted to go from San Francisco to Phoenix, right? Because the compressed representation, the map, is more useful than the actual details, all the details of everything that happens between here and Phoenix. Okay, I'm going to skip over the PCA story and get to some applications here at the end. What does this look like in real data problems? Maybe I'll just get through one. So this here is a model introspection problem. So in this case, this is from a client. This is health insurance claim data. And so in the data set, there are 10,000 points and 40,000 columns. Okay, so it's not a huge data set, but there's a real imbalance between the dimensionality and the number of points. And what they were interested in is doctors who were committing fraud. And what you see here are the doctors characterized by the insurance claims that they submitted, and then it's colored by the cost, the cost of the claims. The average cost of the claims. So there's these groups. The red, these are doctors that are very costly. You have sort of tight red areas. These are, well-defined specialties. You have these kind of webby red areas. These are areas where there aren't a lot of doctors that are like that doctor, right? So this is like revealing the structure, the implicit structure of specialties and how doctors are doing their practice. So they built this model of determining anomalies, of determining cost outliers to try and figure out who might be committing fraud. And what they actually did is they built an ensemble of these anomaly detection models with the idea that the different models would behave independently, right? And they could use this ensemble to determine who was the actual outlier. So what I'm going to do now is I'm going to color this network by the ensemble model scores. And what you see is that the models were consistently flagging this one group of doctors at the bottom for being cost outliers. Now, cost isn't used anywhere in this network creation. That cost, the fact that all those doctors are being flagged, right, those are similar behaving doctors that all the models are saying are fraudulent. So you could say, well, maybe we have a kind of a way of identifying fraudulent doctors without ever looking at the cost, right, the value of the claims they submit to the system. Well, that's one possibility, but what actually happened here was that the models all had a bias in them, right? And it was a bias that nobody had thought to look for because it's hard to understand, right, in this kind of very high-dimensional space, right, that there even are sort of groups of flagged doctors that are kind of close to each other, Right? There are flags elsewhere in the space. You see it's kind of this light green color. So it's not that just that group was flagged, but that group was really sort of preferentially flagged in a strong way. And this represented for this client, they were able to go back and see that they had a strong model bias. Right? And that came out of the summary. All right. That's it, unfortunately. Thank you.